showing you the exact algorithm that trained AI to beat humans in complex games like Go and StarCraft. We will cover the core idea of teaching by experience, the concept of maximizing long-term rewards, and the revolutionary technique used to align large language models, reinforcement learning from human feedback. Deep reinforcement learning can be thought of as the marriage between deep learning and reinforcement learning. This combination showed that a single algorithm training method could allow AI to play many Atari games better than humans. This is the same foundation that powered AlphaGo, an algorithm developed to exceed human performance in the complex game of Go. Reinforcement learning is even used for multi-agent strategy games like StarCraft and Dota. While classic supervised learning teaches by example, reinforcement learning teaches by experience. If you had to remember in one sentence what RL is, it is making good sequences of decisions. The model learns not by being shown the right answer, but by experiencing an environment until it figures out the best actions. In this process, an agent interacts with an environment, performs actions, and observes new states, ultimately receiving a reward. The goal is to maximize the rewards. The agent seeks to maximize its long-term return, which is the sum of rewards with a discount factor. The discount is a very important concept and stays between 0 and 1. To track how good an action is in a given state, we use a structure called a Q table, where every entry represents that value. If the Q table is known, the agent selects the action with the highest value. This value is computed using one of the most important concepts in RL, the Bellman optimality equation. The value of taking an action equals the reward plus the discounted value of the best next action. However, in real-world problems like Go, the state and action spaces are far too large for a simple Q table. Instead, deep Q learning uses a neural network to represent the Q function. The network takes a state as input and outputs the values of possible actions. Once the model can estimate action values, the next challenge is deciding how to choose actions, known as exploration versus exploitation. If the agent only chooses the best known action, it may get stuck in a local minimum. To solve this, randomness is introduced. With a probability called epsilon, the agent takes a random action to explore new states. These concepts are now vital for aligning language models. Language models are trained using next token prediction, but online data doesn't reflect helpfulness or politeness. The model has no concept of good or polite responses. This is solved with reinforcement learning from human feedback, or RLHF. First, a reward model is trained using human preferences, where humans compare two responses and indicate which they prefer. This reward model assigns higher rewards to preferred responses. In this setup, the language model is the agent, the next token is the action, and the reward is estimated by the reward model, given at the end of the sequence. The model updates itself to produce higher scoring, more helpful answers. The concepts of maximizing discounted long-term reward and learning through experience are why deep reinforcement learning drives some of the most impressive AI achievements today.